Most of us picture the start of life in our solar system as an exclusively Earthbound event. But if we rewind the clock far enough, our pale blue dot wasn't the focal point at all. Planets don't generate their own internal heat indefinitely. They have to cool down to support liquid water. Because Mars is significantly smaller and sits farther from the Sun, it reached that ideal temperate state millions of years before we did. It had flowing rivers and wide freshwater oceans. At that exact same point in history, Earth was a furnace of boiling magma. At the dawn of the solar system, the conditions for habitability had arrived on Mars millions of years before they were even a possibility on Earth. The trajectory of both planets fractured at roughly the same time. A massive asteroid slammed into the Martian surface, releasing kinetic energy equal to thousands of nuclear detonations. The force of the impact ripped away the upper layers of the planet. Any primitive microbial life taking root in those ancient oceans was wiped out as the surface instantly vaporized. Earth suffered its own catastrophic collision during this exact same era. Another planetary body smashed right into us. But the debris from our collision didn't scatter uselessly into the void. It coalesced into the moon. Random cosmic violence left Mars stripped of its atmosphere, while Earth's collision provided the gravitational anchor that would keep the planet steady for eons. Mars didn't die quietly. Heat trapped deep underground forced its way out through massive volcanic eruptions, throwing steam and water vapor into the atmosphere to form heavy clouds and rain. The physical scars of that geological push are still there, preserved in the form of Olympus Mons. To understand the scale of that internal heating, you have to look at our own planet's highest peaks. Everest is massive, but Olympus Mons is 3 times taller. But the recovery stalled out. Mars lacks a massive moon to stabilize its tilt, and its gravity is simply too weak to hold on to a thick atmosphere. Without that atmospheric pressure, the surface temperature plummeted, and the newly formed rain froze solid. We know this happened because our rovers are currently sitting right on top of the evidence. They've mapped out the dried riverbeds and deep gorges carved by water that hasn't flowed in eons. Once that internal heat dissipated, the temporary freeze locked in. Mars became a permanent, icy desert. Earth's new lunar anchor locked our access at a steady tilt, creating stable seasons. In warming oceans, bacteria thrived, pumping oxygen into the sky. Ultraviolet radiation struck those molecules, recombining them into a dense barrier, the ozone layer. That chemical shield absorbed the lethal solar radiation. For the first time, living organisms could safely survive outside the deep protective waters and migrate onto dry land. Primitive biological life engineered the atmospheric shield required to build a complex, land-based biosphere. What followed was an incredibly long stretch of biological stability. For 160 million years, giant reptiles sat at the top of the food chain. Then, a massive asteroid crashed into the Earth, igniting the atmosphere, blocking out the sun, and plunging the planet into a temporary burning hellscape. That mass extinction was a harsh but necessary biological reset. It cleared out the massive apex predators that consumed everything in their path. With the giants gone, smaller mammals had the space to survive and adapt. Over millions of years, the surviving species prioritized brain development, problem-solving, and tool use over physical size. Our capacity for intelligence was made possible by the impact of a random rock falling from the sky, at a moment when it changed the entire evolutionary trajectory. We often behave as if our intelligence makes us permanent fixtures here. Yet, we've built a world where a synthetic virus or a nuclear exchange could end our species in a matter of hours. Even if we navigate our self-destructive tendencies, the solar system itself has a fixed expiration date. Our sun is a finite engine burning through its internal fuel. As that fuel depletes, its core will destabilize and outer layers will expand. The math is unforgiving. When the sun's volume swells by just 15%, the Earth's oceans will boil away entirely. The planet will turn into a heated oven. Eventually, the expanding solar mass will swallow the Earth, melting the crust and returning the planet to the lifeless state of its neighbor, Mars. Planetary destruction is a mathematical certainty. Our existence is a brief, improbable window of stability
in a cosmic timeline defined by change.